Hello viewers and welcome to another episode of Space Science with Python. As you see in the title, today is a concept video, so we will not dive into the coding part, but we will talk more about some deep learning architecture, namely autoencoders, that we will then code in our next sessions. And for all the viewers that just joined these tutorial sessions, so the link is in the description of my GitHub repository with all the different sessions. And here in this machine learning project part, ML1 asteroid spectra, we have now 10 Jupyter notebooks that can be used to recreate all the machine learning topics for our asteroid spectra. Now, for all the viewers that don't know what asteroid spectra are, I will just explain them just in a moment. Just note that all these notebooks here, they have a Google badge on the very top. So you can simply click on it, on the badge. Where is it? There. And it opens then in Google Colab automatically. And then I would suggest to have also a Google Drive account where then all the data are being stored in your Google Drive. So yeah, this is everything you just need for our machine learning project. The first three scripts are the most important one to fetch the data, to parse the data and enrich them. The other one are optional for the machine learning part, the spectra viewer and so on. But all viewers that are new to this tutorial, I would suggest to go through all the Jupyter notebooks and markdown cells to get an idea what's going on. And in the last sessions, we developed some algorithms to create a classifier for our different classes. We used support vector machines. We used the fully dense neural network, a convolutional network, and also in our last tutorial, we used Keras tuner to tune our convolutional network. Now it's very unfortunate that the 10 is now on the top. I should have called it 01, 02, and so on. But lessons learned for the future project videos. Now, let's move to our autoencoder architecture and our task that we would like to tackle in the next video. So I was a little bit confused now. I don't know why. Let's draw a spectrum. So what do we have on the very left side is an X and Y axis. The lambda is the wavelength of our light. So a small number like 400 nanometers corresponds to higher energies and a blue light. And on the right side, we have like, let's say 700 nanometers corresponding to less energy and a more reddish color like red. And the asteroid reflectance spectra data we are using are within this visual spectrum range. So between blue and red light. And the asteroid reflectance spectra, what does it say? It says it indicates the percentage of light that is being reflected of the surface of the asteroid depending on the wavelength. So let's take an example. Let's draw some random line like this one. And this says, so let's assume a larger R means a larger reflectance. It means that a value that is, for example, here, let's say it's a green light, is reflected way more efficiently than light that is being reflected here, which let's say is yellow light. Yeah, this is just some random example. And our classes we had in the asteroid data were so-called C for carbonous asteroids, stony asteroids for S, the iron-like asteroids X, and the others. And of course, there are different sub-classifications depending on the classification system you're using. But in our case, we simply use these four classes C, S, X, and others. Now, with Keras, we created our classification tool where we simply said, okay, we have a spectrum that looks like this, a spectrum that looks like this, a third one looking like this, and then we have a different class that may look, for example, like this. Here, this is our second class. Let's say this is class 2. This was class 1. And we created a classifier with support vector machines and also with neural networks to classify the input spectrum to assign the spectrum to a certain class with our training data. So we trained it and then we use our test data to see whether our classifier worked properly or not. Now the spectra itself, let's erase everything and redraw our initial spectrum. This had like a lot of individual points. So of course, the discrete data. And in total, we had 49 data points. Now, the question is now, okay, how can we map the data, or how can we create some kind of unsupervised learning? So it's some kind of dimensionality reduction where we see the differences between the different spectra in a lower dimensional space. How is this possible? And there are different methods and ways. And one method is the so-called autoencoder that I would like to show you today. So the autoencoder is, in theory, quite simple. Let's take 5 neurons as an input. So 5 neurons here. We have a second layer with 3 neurons. I know this is like very simple, but you get the idea. It's just some schematics. It's fully connected, but I'm not drawing it now. Let's keep it simple. So we put our spectrum here in this neural network, and the neural network compresses the information. So the number of weights and the number of neurons decreases with more layers until we reach a certain point in the middle. Yeah, so this is like these two blue neurons. And these two blue neurons contain the most compressed information of the spectrum. And then afterwards, we are increasing the size of the neural network again. Let's say again 3 and 5. And let's connect it also here quickly. Yeah, something like this. Oh, a 5th neuron. Yeah, and the output of this neural network is our initial spectrum itself. So yeah, this is like our spectrum as we drew it in the beginning. So here also mapping 49 points. You may say, okay, cool, this is really boring. I have a signal, I put it in a neural network, and as an output, I get the same signal. So what's the idea? Well, the idea is quite interesting because the information of the different spectra that we use for training, they are propagating through this neural network. And while we are training this neural network, the information is being compressed. So from the very beginning, the information is compressed until we reach these 2, let's say, blue neurons. And then the information from these 2 blue neurons are then used to decode the information in a way that we recreate our initial signal. So it's a regression problem. Our signal is the input, and our signal is also the output. So let's say we have a data point that is called, I don't know, let's draw something, take a different color. We have here a data point that is here at lambda 1, mapping R1. So this value goes through the neural network, and the output should be the same value. So again, lambda 1 and the corresponding R1. So regression problem, a data point becomes the same data point again. The interesting thing is now that due to this compressed algorithm, due to compressing architecture, we can use it for different things. Like, for example, if you imagine, for example, images of dogs again, yeah, and the dogs images are very noisy, and we put it through the neural network of course tries to compress the information as good as possible, so it trains the most relevant information that makes this dog image in dog image, and because we are compressing it, it cannot remember or train all features in there. And one feature that is then probably not important for this image is the uncorrelated noise. So you can put a noisy image in this neural network, and as an output, you get a not so noisy image. So maybe the resolution is a little bit worse, but the noise should be gone. Now, we can use this network, of course, also for our asteroid spectra, but what we can do is we can extract the information here in the middle and visualize it. Yeah, so let's assume our 49 dimensional data points, 49, are compressed to a 2-dimensional space. Of course, this is a compression of a factor of 25, so this is ridiculously high, but let's assume it works, and we have here now 2 values. let's call it encoded value 1, encoded value 2. And then we have different classes. So for example, this spectrum here appears in this space, in this two-dimensional space somewhere here. Now we use the same, another spectrum of the same class. It may appear here, 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 and so on. Then we use a different spectrum type. It appears here, 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 here. And then maybe a third class that appears somewhere here. Of course, I just said unsupervised learning. In our dataset, we have the information of the labels, so it will help us to get an idea. But we will never use the labels for the training itself. It's just for the visualization purposes. And then afterwards, when we have this low dimensional space, we can then, for example, cluster them with some clustering algorithm to see whether these different classes are also visualized in some low dimensional space. Now, in our next video, we will not directly start with this clustering algorithm, because for the clustering algorithm, I would like to work in maybe 5 or 6 dimensional space. Otherwise, the information compression is too bad, I would say. To get an idea whether compressing information from 49 dimensions to 2 dimensions and then back mapping it to 49 works, is something that we will cover in our next video. So in our next video, we will create an autoencoder where we feed it with our spectra, and we create an autoencoder that has a latent space of 2 dimensions, not for any machine learning purposes or classifications, but just for the purpose of visualization. Yeah, so we just want to have an idea. I mean, the results won't be that good, but let's have just an idea whether we see some kind of separation or clusters in our data. Yeah, to get a feeling and understanding how to create such a network. And then afterwards, we will create a network that has 5 or 6 or 8 dimensions, and then we will use other algorithms to cluster them. But the clustering algorithms will also be explained in another concept video. For now, let's stick with this autoencoder concept. I hope you still have some time to go a little bit through the coding parts from last time. And next time we will then have our 11th Jupyter notebook where we are starting to create our autoencoder. So I hope you like this concept video. I mean, it was a little bit of drawing. It was a shorter video, but I think it's quite important to separate maybe theory from coding, so it's not too confusing and you can prepare a little bit for the next time. So just let me know whether this kind of videos are helpful at all, or whether they are extremely boring or even bad. I mean, I'm not the best, I'm not a CGI expert or so. I'm just doing it here like in a seminar, like in the university, showing my drawing skills. Okay, cool. So let's continue with some coding next time. And until then, I wish you a very nice week and hope to see you next week in our coding session. Until then, take care and see you next time.